Okay, let's continue the class. Okay, and in the previous part, we looked at the process of handling a page fault event. Okay, and when page fault event happens, a victim may need to be chosen. Uh, when there's no free frame, the operating system needs to choose a victim. Okay, and then which one becomes the victim is a very important decision. Okay, and here you are looking at a list of algorithms for choosing such a victim. Okay, and whether or not a good victims are chosen really decides the performance of the system. Okay, and here the performance is reflected by this number. Okay, page fault rate. Okay, how often page fault happens. Okay. Okay, the first algorithm of FIFO, first in, first out. Okay, and is a very simple algorithm. It's very easy to understand and implement. Okay, and that is the longer a page stays in the physical memory, the more chance is going to be chosen as the victim. Okay, and very simple, and but is not a very good algorithm because and it gives no consideration to how active this specific page is. Okay, so FIFO may really swap out a page that is actively being used. Okay, and is suppose this page stays in the memory for a long time. Okay, and but this page stores a piece of code that runs for many iterations. Okay, so this page is a long residence of in the physical memory, but it isn't really needed. Okay, and choosing this one as the victim. Okay, and may hurt the operating system's performance because this page once is chosen as a victim. Okay, and very soon later this page may be needed again. Okay, and when that happens, the operating system needs to load this page back. Okay, so storing one page to the disk and then need it again and then loading it back sounds very silly. All right, so not a very good algorithm. Okay, and the next one is a very good algorithm, that is the optimal page replacement. Okay, and which says the victim is the one referenced in the furthest future. Okay, so this victim needs to be the one, okay, that is not needed, okay, in the near future, and actually compared with other pages, this one is needed in the furthest future. Okay, and this one can be proved to be the optimal in terms of having the lowest page fault rate. Okay, and but you can easily tell that this algorithm is not very easy to implement. Okay, and because it requires the operating system to know the future. Okay, which is impossible. Okay, and this is something that we often do in computer science. Okay, if we do know the future, we use the historical data to predict the future. Okay, so here the algorithm says, okay, and the victim should be the one that is needed in the furthest future. Okay, so this is unknown. Okay, but we can find a measure, okay, to predict this future. Okay, that is the least recently used LRU algorithm. Okay, it's not exactly the reflection of this optimal algorithm, the furthest future, okay, algorithm, but is approximation. Okay, so the idea is, I'm sorry, then the idea is the page that it has been used the least, okay, in the past, okay, should be the one that is needed in the furthest future. Okay, which may be reasonable. Okay, but it may have, there may be some exceptions. Okay, but this is the best we can do. Okay, so and this LRU algorithm is used in many operating systems. Okay, and it has been shown that this algorithm is pretty good, okay, and but how this algorithm is implemented is a really big deal, okay, and the primitive way of doing that is, okay, and every page needs to be time-stamped, okay, and every time a page is referenced, no matter it's reading or writing, okay, this page is going to be time-stamped, okay. So then when it comes to the operating system needs to choose a victim, okay, and those timestamps are compared and see which one shows the earliest time, okay. So as you can see that this implies searching, okay, so searching may be needed, okay, so it could be more expensive, okay, than FIFO, right? Okay, so so the most primitive implementation is this based on counter implementation, okay, and each page table entry is associated with a time of user field, okay, and once a page is referenced, this field is updated and with the system clock register, okay, and then at the page replacement, the victim should have should be the one with the least time of use, okay. So as you can see that the as every time page fault happens, the operating system needs to scan the list of pages in the physical memory and choose the one that hasn't been used for long, okay. Okay, so a very easy to understand algorithm implementation of the algorithm, okay, but it may be expensive, okay. Okay, and this is another one called based on stack LRU, okay, and is a very good implementation in terms of avoiding searching, okay, and the idea is all we need to know, the idea is we allocate more space, okay, and we keep track of, okay, who is the one that hasn't been used for long, okay, and the data structure in the background is a stack, okay. Okay, so here, and I'm going to switch to an Excel spreadsheet to show the logic of this algorithm, okay, and here is something that I want to clarify, okay, and here says a reference string, okay, and which is a sequence of numbers, okay, and those numbers are frame numbers, okay, and so this 4 means physical frame 4, okay, this 7 means physical frame 7, okay, so in other words, okay, and the 7 so basically this string tells us the record of page reference or frame references, okay, so and as you can see that some of the frames are accessed multiple times. Let's say 4 is accessed here, and okay, 4 is only referenced here, okay, and 7 is referenced here and here, and 0 is referenced here, and 4 is referenced 4 times, okay. Okay, now let's switch to this Excel spreadsheet. Okay, so here this highlighted row shows those frame numbers, okay, and every time a frame is referenced, okay, this frame number is going to be pushed on the stack, okay. So initially, let's suppose that the stack has nothing, okay, so the first frame number is 4, so 4 comes to the stack, okay. Okay, so and the next frame number is 7, and so 7 will be pushed on the stack, so 4 is still the bottom of the stack, and now the stack gets 7, okay. So now with these 2 numbers on the stack, and we can easily tell that the bottom of the stack is the one that was referenced the earliest, okay. So now suppose the a victim needs to be chosen, okay, we need to choose 4, okay, pretty clear, right? Okay, so given this stack being this way, okay, the next one is 0 in the list, okay, So the stack has already got a 4 and the 7. Now it has 0. Okay. Okay. So now if a victim needs to be chosen now, it's going to be 4. Okay. Okay. So the next one is interesting. That is 7, and the 7 is already on the stack. Okay. We cannot push the same number on the stack multiple times. Okay. And the 7 in this case, okay, shows, okay, 7 was referenced before and now is referenced again. Okay. And so 7 should be the most fresh page on the stack. Okay. So 7 should be on the top of the stack. Okay. The bottom of the stack is the one that hasn't been used for the longest, and top of the stack means a page that was just referenced, right? So now what happens is, in addition to the traditional push and pop stack, okay, now what we're going to do is we're going to pull 7 out of the stack and then let a 0 fall on 4, okay, and then re-push 7. So now what happens is, okay, 4 still on the bottom of the stack, and the 7 is going to be removed from the stack, okay, and then 0 falls on 4, and the 7 is re-pushed on the stack. Okay, so so now 4 is still at the bottom of the stack, and the 7 is the most fresh page on the stack. Okay. Okay, so as you can see that the this stack, okay, in addition to push and pop, there's another operation associated. Okay, and the way how this operation works implicates that this stack needs to be implemented as a linked list. Okay, if it was implemented using an array, okay, and then we may need to do compaction or shifting. Okay. Okay. All right. So next one is a 1. Okay, and what we're going to do is we're going to keep 4 and a 0 and a 7, and then 1 comes at the top. Okay. Okay. Next one is a 0. 0 is already in the stack. Now 0 is going to be pulled out. Okay. So we're going to let 4 stays and 4 stays. Okay. And then 7 and 1 fall on the stack on top of 4, okay, and 0 is re-pushed. Okay. Okay, next one is 1, okay, and 4, 7 and 1 stay. I'm sorry, 4, 7 stay, and then 0 is out, and I'm sorry, 1 is out, and then 0 falls. Then 1 is re-pushed. Okay. The next one is 2. So that we have 4, 7, 0, 1, and a 2, because 2 is a newcomer. Okay. Okay, and then 1. Then we have 4, 7, 0, and 1 is going to be removed, and 2 falls on top of 0, and the 1 is re-pushed. Okay. Okay. Then showing another example, we're gonna switch back to the PowerPoint slides. Okay, and next one is 2. 2 is already in the stack, so we have 4, 7, 0, and 2 goes away, and 1 falls, and 2 is re-pushed. All right. Okay. Okay. Now let's go back to the slides. Okay, and here shows another example. Okay, and these 2 stacks are reflect the history before and after 7 is referenced. Okay, and this stack shows, okay, the numbers, okay, 4, 7, 0, 1, 2, and those reflect the order of references before 7 is referenced. Okay, and after 7 is referenced, 7 will be put out. Okay, and 0, 1, 2 fall on 4. Okay, 0, 1, 2 will be falling on 4, and the 7 is re-pushed. Okay, so here is the stack before and after 7 is referenced. Okay. Okay. Okay, I feel so strong to ask any questions, but I need to realize that this is pre-recording. Okay. All right. So given this data structure, the bottom one is the least recently used page. So every time if a victim needs to be chosen, the bottom of the stack needs to be removed. Okay, so just a couple additional remarks on this algorithm. Okay, and so suppose the system now needs a victim, so 4 will be chosen as the victim. So as long as the 4 goes away, and 7 will become the victim in the next time, unless 7 is referenced again. Okay. Okay, and another remark is okay, and this algorithm really needs the operating system to know where the representative of a specific page is in the stack. So suppose given 7, the operating system needs to know 7 is here in the stack. Okay, so this would require the page table to have another record that is a pointer to the representative of this page on the stack. Okay, so again, this using this data structure would require the operating system to update the page table structure. Okay, all right. Okay, and obviously this based on stack implementation requires no searching. Okay, because the bottom of the stack is always the victim, is always the least recently used page. Okay. Okay, and as you can see that this data structure needs to allocate a space. Okay, and every time a page is referenced, this page may need to be pulled out from the stack if it was already referenced before. Okay, and this data structure needs to be implemented as a linked list. Okay, so the updating on the pointers may incur more memory access unless this data structure is cached in the CPU. Right? Okay, and another one is is not a exactly implementation of LRU algorithm. Instead, is a approximation. Okay, that is called a second chance algorithm. Okay. Okay, and this algorithm is actually a combination of LRU and FIFO. Okay, first in, first come. Okay, and the data structure in the background is a circular queue. Okay, and let me first jump to the graphical demonstration. Then we go back to see the description in words. Okay. Okay, so in this implementation, okay, every page is associated with a reference bit, okay, and if this reference bit says 0, that means this page hasn't been referenced. Okay, and if this bit says 1, that means this page has been referenced. Okay, it's a binary basically. Okay, okay, and meanwhile there is a victim pointer. This pointer points to the page that will be chosen as the victim. Okay, okay, so every time a page is pointed to by this pointer, and it will become a victim. Okay, and then this pointer will move along the list of the pages in a circular way. Okay, okay, so once the pointer points to a specific page, okay, and this one is going to be the victim, but another part of this algorithm says, okay, and the operating system may forgive this page if the reference bit says 1. Okay, so the reason why is because this page being tested has been referenced before. Okay, so the operating system would consider, okay, this page was just referenced. Okay, it may be referenced again. Okay, so the operating system is going to forgive this page for now. Okay, and but the operating system will, in addition to leaving, okay, this page, it will flip this page, flip this bit. Okay, so basically the operating system sends a message that, okay, I can forgive you now, but you have to be referenced again. Otherwise, the next time I come to you, you will become the victim. Okay, so as you can see that in this example, this pointer points to this page, and whose reference bit is 1, so the operating system is going to forgive this page, then move on to this page whose reference bit is always 1, is also 1. Okay, so this page will be forgiven likewise. Okay, so then the pointer will move to this page. Okay, then this page is a reference bit is 0. Okay, so this one will be chosen as the victim. Okay, so here shows this case. Okay, now the pointer points to this page whose reference bit is 0. Okay, so the operating system will choose this one as the victim. Okay, so once this one goes away, then this pointer will keep moving. Okay, and then sooner or later, this negative, the next victim pointer will be moving back to these 2 pages. If the reference bits for these 2 pages are still 0 and 0, okay, they will be claimed as a victim. Okay, so in order for either of these 2 pages to survive another scan, okay, these 2 ones need to be referenced. Okay, so that's the reason why the name of this algorithm is called a second chance algorithm. Okay, so now let's see the description of this algorithm in words. Okay, and so this algorithm is a combination of LRU and FIFO, and the data structure being used is a circular queue, and a pointer is used to indicate which page is the next victim. Okay, and each page is associated with a single reference bit. Okay, and if it's set every time the page is referenced. Okay, and a victim may survive, and if its reference bit is set. Okay, and in this case, this victim will be given a second chance. Okay, and its next in the queue will be considered as the victim. Okay, so a page shouldn't survive the second time without another reference. Okay. Okay, and the reference bit is supported in many systems because it's so simple, and all the page table needs to be revised. Is it needs to add another bit to page table records. Okay. Okay, and the last part of this discussion is page buffering algorithm. Okay, and here is the idea. In the physical memory space, there are some pages being reserved. Okay, and those pages, okay, don't participate in allocation. Okay, and instead, okay, those pages are only used in page replacement. Okay, so in other words, okay, when a victim is needed, okay, and the operating system is going to choose from the free space. Okay, so in that case, a victim is in the free space. So because those free space are already pre-allocated, okay, and they do have their copies in the hard disk. Okay, and so then the victim do need to be swapped out to the disk. Okay, for now. Okay, and instead, okay, those victims can stay in the physical memory, and when the system is idle, those victims can be swapped out. Okay, so this will delay the action of swapping out a victim. Okay. Okay, let's see how much time it has taken. Another 24 minutes. Now let's take a break.